So this section is on the Earth, the Moon, and the sky. And let me see if I can pull up the right section here on the screen. There we go. Some of this vocabulary we've seen already: right ascension and declination, latitude and longitude we'll talk about here a little bit. Lunar eclipse, meridian, phases of the moon, sidereal day and synodic day, sidereal month and synodic month, synchronous rotation, and tides. We'll also talk about seasons and things like that. And so let me first pull up some of the figures, and we can just talk about some things we've already sort of talked about. This is another picture of latitude and longitude. This is how we measure it on Earth. The latitude, we looked at these a little bit in the last chapter. The latitude is the angle in degrees you are up from the equator, and the longitude is how far you are east or west from Greenwich, England. From that longitude line, the longitude lines go up and down, the latitude lines go kind of left and right, you might say. If you ever go to Greenwich, England, you can stand on the line that's 0 degrees longitude. That's kind of fun today to do. The right ascension and declination are very similar, except they're for the celestial sphere, and so instead of marking them by places on Earth, we mark them by places in the sky. And we talked a little bit about that last time. 0 degrees is sort of the direction that the sun is in on the 21st of March, basically at the vernal equinox. And then we measure east and west from that, and we measure we measure east and west for right ascension, and then declination is the angle similar to latitude that we are away from the north or south on the celestial sphere, away from the celestial equator. And that gives you, that way you can identify the position of every star in the sky, and they always just stay at that spot, of course. But the planets drift through the sky, so their right ascension and declination are constantly changing. Let me see if I can pull up another picture here. So the Earth is rotating, it's on its axis, the Earth is round. We've already talked about a few ways that we knew the Earth was round. The ancient Greeks figured out that the lunar eclipse is the shadow of the Earth on the moon, and that's always got an arc in it. We saw it last time. We also know that at different latitudes there are different stars overhead. That's also a big clue that the Earth is round. This was invented by a guy named Foucault. It's called the Foucault pendulum, and it's a very long weight hanging on the end of a very long string, and basically the Earth is rotating underneath it. And so if you set it up just right, and it can swing for a long time, as the Earth rotates through a day, it will keep knocking down these little candles or I don't know what those little objects are, but sometimes they'll have it put out candles as it's swinging back and forth. These are just little things that it gets to knock over. Lots of museums have these. There's one in the physics building at the University of Oklahoma. If you ever go to Norman, you can just go into the physics building and see it. So it's yet another way to show that the Earth is round and rotating. So this is a picture of the Earth as it's rotating, as it's orbiting the sun. In addition to rotating, it's orbiting the sun. So what you see here, this axis of the Earth, is its rotational axis, and that is tilted with respect to the ecliptic, which is the plane of its orbit. And so sometimes the Earth is tilted. The North Pole, that's the top one here, is tilted away from the sun, and sometimes it's tilted toward the sun, as it is over here on the left. And so when the North Pole is tilted most away from the sun in this position, this is called the winter solstice. And in the northern hemisphere, that's the shortest day of the year. Santa Claus, who lives right at the North Pole, doesn't get any sunlight on that day. Neither does anyone who is within 23.5 degrees of the North Pole. The southern hemisphere gets summer at that time. The winter hemisphere the northern hemisphere gets winter at that time. And then this is the vernal equinox, and now the tilt is sort of kind of parallel, you might say, to the direction of the sun. That is, the northern and southern hemispheres get the same amount of sun. It's spring in the northern hemisphere, and fall in the southern hemisphere. And then in June, now the North Pole is tilted directly towards the sun, or as close as it gets to tilted towards the sun. And we get extra long days in the summertime and extra hot, and they get winter in the southern hemisphere, and so on with the autumnal equinox. And so seasons actually depend on how you're tilted towards the sun, and I'll show you a little bit more about that here in a second. In fact, the Earth is actually closest to the sun in its orbit in the winter, sometime in January. Even though those are cold months for us, we're actually closest to the sun by distance, but that's not what matters. What matters is the tilt. And so I'm going to show you a couple of pictures here in just a second. So if you look at this picture, this is where the northern hemisphere is tilted toward the sun. And so this is the summer solstice. Notice that the sun is bearing down almost directly overhead. If you live in Oklahoma, you're getting not quite overhead, but close to overhead sun in the summertime in Oklahoma. And so if you look at so here's a flashlight, right? And I'm going to just shine a beam down like this. And so you can see that the circle that beam makes. Now if I tilt the circle, holding it the same height, you can see that the area of the circle gets bigger. And so when the sun is lower in the sky, and the beam comes in tilted, the sunlight, instead of getting compacted in an area, gets spread out, and that reduces the amount of heat you're getting, and so you get cooler weather. In the same way that in the daytime the sun is less hot at sunset, right, when it's kind of skimming along the ground, than it is when it's directly overhead. Seasons kind of work the same way. And so the reason we have seasons is because of the tilt in the Earth's axis. In the summertime, if you're in the northern hemisphere, in the summertime, you're getting a more straight-on look at the sun. And if you're in the northern hemisphere in the wintertime, when Oklahoma rotates it around, it's up here, you're getting a much more slanted look at the sun. And so the rays are spread out much more, and you don't get nearly as much sunlight. Also, the day is shorter, and so because your Oklahoma moves into the sunlight later in the morning and gets out earlier in the evening, and the rays are at a very low angle in the sky. The sun makes a very low angle in the sky. And so the consequence of all that is it's cold in the wintertime. And it all has to do with the tilt in the Earth's axis. Here's another picture of the tilt, the rays. In the summertime, the maximum angle is about 73 degrees, roughly at our latitude. In the wintertime, it's much lower, so the rays are spread out much more. It's not as warm. And so seasons have to do with the tilt in the Earth's axis. If the Earth's axis wasn't tilted, we would get no seasons. This is a picture as viewed from somebody standing on the Earth, watching the sun come around the rise and set. And so the person standing on the orange platform there, that's just kind of them standing on the Earth, and that's their horizon. At the summer solstice, the sun rises north of east, so you should get up nowadays and notice that. The sun rises way north of due east. It comes across the sky. It's actually south of directly overhead at noon, and then it sets north of west. And so it follows this arc in the sky. At the equinox, so in mid-March and mid-September, it rises and sets right on the eastern and western directions. And you should notice that when you're driving. When you're driving, you should notice that at sunset in the spring, in March and September, the sun is like right on the horizon. Finally, in the winter, the sun rises south of east and sets south of west, and it's low in the sky the whole time. And so we don't get a lot of good overhead sunlight for heating, and so that's our winter. And so all having to do with the fact that the Earth's axis is tilted. If it wasn't tilted, we wouldn't have this effect. So that's seasons for us. So this is the last thing I wanted to mention about this is you see here the Arctic Circle. So that's the 23.5 degree line. If you're north of that, then on the winter solstice you'll have at least one day of where the sun does not set. So if you were sitting at the North Pole, the sun would not set for a good chunk of the year. But if you're right here at 23.5 degrees, then on one day a year you would get 24 hours of daylight. Similarly, if you were on the 23.5 degree, within 23.5 degrees, in other words, inside the Arctic Circle, on either pole, you'll either get at least one day with 24 hours of night and at least one day with 24 hours of day. And so that's how the Arctic Circle is defined. It's anybody who's within the angle of the tilt of the Earth's axis of the pole. This line here, the Tropic of Cancer and the Tropic of Capricorn, those are the maximum latitudes you can have. Tropic of Cancer is north of the equator, Tropic of Capricorn is south of the equator, where the sun will at least be directly overhead at least one day at noon. And so if you're north of that, like we are, if you're north of the Tropic of Cancer, then the sun is actually never directly overhead. It's still south of your zenith at noon on the summer solstice. And so only between the Tropic of Cancer and the Tropic of Capricorn do you get days with at least one day a year with 24 hours a day, with the sun directly overhead. So I wanted to talk a little bit about a day. So if we draw a little picture of the sun here and have the Earth going around it, say like that. I was trying to make that pretty round. I didn't do that good a job. So this is not a scale drawing, again. And so here's the Earth, right? And if I'm standing here, like that, again, not a scale drawing, what time is it for me? Right? You should say noon, because the sun is directly over my head. This would be midnight, right? If the Earth is turning this way, this here would be sunset, and this over here would be sunrise. Right? And so that's noon. And so I'm going to just erase that a little bit and come back to it. So here is a little circle here. Here's the arc of my... And so if we wanted to define a day, we would say the day is the amount of time between when I have a noon, my head was a little crooked there, right, and the next noon. And so, this is noon, the sun's directly over my head, right, and if the Earth were to rotate once on its axis, then when the sun was directly over my head, one rotation of the Earth would be 24 hours. That would be what we would call one day. Here's what makes it a little tricky, is while the Earth is rotating, it's actually traveling in this direction. And so this is a gross exaggeration, but let's say a day later it's over here, right? So here's my Earth now. Now, for the Earth to rotate once on its axis, then it would be a day when I was pointing straight up, right? Straight up the page. But that's not noon, right? Because noon is when my head's directly towards the sun, right? And so technically the next noon would be over here, right? Do you follow that? Instead of this way, which would be the Earth rotating exactly one time, right? The Earth has to actually rotate a little more than that to get back to having the sun directly overhead. And so when we go from noon to noon, noon to noon is technically a synodic day, and it's longer than the rotational time of the Earth. You try to spell that a little more carefully, since that's the word So it's a synodic day is noon to noon, and a sidereal day is once on its axis. Sometimes they'll say once on its axis relative to the stars rather than relative to the sun. But it's just when it rotates 360 degrees, so these two are different. So there isn't a big difference between a synodic day and a sidereal day. It's about 4 minutes. The synodic day is about 4 minutes longer, but they're not exactly the same thing. And so the words synodic and sidereal will show up again here in a little bit, and they're used quite often. It's the fact that this geometry is weird. By the way, there's lots of weird things going on here. For example, the Earth's orbit is not circular, and so it's moving faster in some places than in others. And that means that even the synodic day is not the same all the way around, because if it's moving faster, it travels more, and then it has to rotate even more to get back to having the sun directly overhead. And so what we call a day, the normal day, is called a mean solar day. And it's the average synodic day over the course of a year. That's the thing we call 24 hours. We call that a mean solar day, and then we divide that up into 24 equal hours, and that's how we keep time for the most part. I'm going to come back to this when we talk about the moon. So let me put up a different picture here. So this is the same thing. This is what I was just talking about, right? By the way, a local noon is when the sun is directly overhead, right? Or it crosses your meridian, I should say. Remember, the meridian is the line that splits the sky. It goes from the North Pole to the South Pole where you're standing through the sky. And that means it splits your sky in half with an eastern half and a western half. When the sun crosses that line, that's called local noon. So I can just write a little bit of this down. And so 200 years ago, that's how every town kept time. When the sun was halfway across the sky, they called that noon. And they keep time off of that. The problem is neighboring towns would have slightly different times, and as people began to get timepieces that worked and began to travel a lot, this business of different towns having different times didn't work very well. And that's why we have time zones. And so, hang on a second. So, mean solar day is the average synodic day over 1 year. We call that 24 hours. Local noon is when the sun crosses the meridian, right, when it's at the halfway point in your sky. And so we divide the sky up, the world up into slices, and we have 3 across the United States. We have 4 time zones technically: Eastern, Central, Mountain, and Western, or Pacific, and we do that so that we have, instead of just everybody having a local time for every town when the sun's on meridian, we have regions that have the same time. And then so it gets earlier and earlier as you go to the west, because the sun's getting to noon late. It takes it longer and longer, because remember, the Earth rotates west to east, so to the right on your screen, right? And so that means it has to be earlier in the Pacific, on the Pacific side of the United States than on the Atlantic side, because noon happens on the Atlantic side before it happens on the Pacific side. And then we have this red line, which is called the International Date Line, and so it gets earlier and earlier and earlier, and then we skip a day forward. And so these people right here are actually a day ahead of the people here, and so Australia is a day ahead of us. But there's also a time shift. So So that's why we have time zones, because the Earth is round and it's rotating